And we're going to do this in terms of alpha and LT bar. Remember, we could do alpha wing body and LT, or we could do it in terms of alpha and LT bar. And so the formula that we had for that look like this. It's the pure couple of the wing, the lift of the wing times the moment arm, the lift of the tail. Sorry, this is the total lift times this moment arm. Remember, it has that other term because of the LT bar that shifts things. This is the lift of the tail times the moment arm there. And then the propulsion. And so now we need to substitute in for CL. And that's easy, that's real short, but the tail has the angle of attack reduced by the setting angle and the downwash model. And we said we're doing things in terms of alpha because of this here, but this is in terms of alpha wing body. So we have to use the conversion that relates alpha and alpha wing body. We did this a couple lectures ago when we factored the A out and got everything in terms of alpha. So you can see we're going to end up with a long expression. We're going to plug in here and here, and then this has to go up here. This has to go up here. So we're going to get a giant mess, and then we're going to chunk it into two parts, and it's going to become easy. You just plug in numbers, and you're good to go. So I'm going to write out after we, let's see, we substitute in, let's see if I wrote the right version there. Yeah, we collect these two together into one term, so we get 1 minus d epsilon d alpha times alpha wing body, and then we substitute it in there. All right, so I'm going to leave this up. I'm going to shift over there. You guys done with this? So I can make sure that the people on Zoom are good copying. So here's the big thing we get. So you can see straightforward where that comes from. We plugged that in, so that's where we get that first term. The second one comes from factoring out the 1 minus d epsilon d alpha times alpha wing body, and then we stick all this stuff in. And we still have the propulsion to do. So we're going to come up with just a real simple model for our propulsion. We're going to say, well, this is the pitching moment of the propulsion. And then there's how the pitching moment changes with angle of attack. If you remember, it makes sense because the thrust line was at an angle gamma of the engine, and then the angle of attack was here, so the component of the thrust could vary with angle of attack. It can change. So we'll just throw that in. So that's what we add on the end here as far as the propulsion stuff goes. And in all honesty, I'm including it so that you can see, well, yeah, the engine could produce a pitching moment. For most of the examples and the stuff we do, we just say that that's zero. That the thrust line is not tilted up so much, it's pretty much just straightforward through the CG, and that the drag is backward, and so the thrust just balances the drag, and you get no moment. So this is a big, long formula. But if we look at it, it's just the equation of a line, believe it or not. It's, does that show up on the board? That shows up okay, doesn't it? We're going to end up with a part that does not multiply angle of attack. And then we're going to end up with a part that does. And so the reason I pulled out the other color is I'm going to circle all the alphas and where they show up. So that's the stuff that's going to go in here. And everything else that does not multiply alpha goes in here. And then we're going to call this CM0. It's the pitching moment at 0 angle of attack. And then this is the change in the pitching moment with respect to angle of attack. It's the slope. So let's fill in those terms. And I'm going to have to go a couple lines here, so let's put this in. So that's all the stuff that does not multiply alpha. And then here's all the stuff that does. And the definitions of this thing here and this thing here in terms of essentially these formulas are on page 32 in your text. And that's another page that maybe you put a paperclip on. Remember I said paperclip the axis? So put a paperclip on this because you're going to want these formulas all the time. Now also on page 32 is the other version in terms of alpha wing body and LT. Remember I said this was in terms of alpha and LT bar, which shows up here. So we could do exactly the same thing in terms of alpha wing body and LT. And so there's another set of formulas on this page here that do that. And so let me shift over to the other screen. Give you a second to get caught up. I know this looks like a giant mess, lots of terms, but if we're designing an airplane, we actually know all the stuff that goes in there. Let's look at it. We're building the wing, so we'll know the pure couple of the wing. We'll know the lift curve slope of the wing. That comes from the big formula. We know the locations, so we know all that stuff. That all goes into these formulas here. We'll know the area of the horizontal tail and the area of the wing and where it's located. We'll know the lift curve slope of the tail because we'll use the big formula on that wing. We'll know the lift curve slopes here. We'll know the areas. We just talked about that. We'll know the angle that we set it at. We'll know the downwash model. So all of this stuff, eventually, when you calculate it, you just plug in all the numbers that we calculate in the locations, and so you just get a number here. And the same thing here. CM0 is going to be a number that depends upon the configuration and the geometry of the airplane. So as I was saying, on page 32, there's also a version in terms of alpha wing body and LT. And it looks like this. And so that's in terms of alpha wing body and LT. And then the other formula we have over there is in terms of alpha and LT bar. And in fact, CM alpha is the same. It's that same formula. If you do it either way, it's the CM0 that changes. So does anybody notice anything that bugs you other than there's a lot of terms about what I just wrote? Is there anything that seems kind of odd? So which formula uses LT bar? Bottom one. Which formula uses LT? Top one. And yet LT is in CM0, but look, there's a CM0 bar. So that you should be saying, what the heck, did I put the bar on the wrong one? I didn't. In your textbook, this is how he does it. Bugs the heck out of me. If I were writing this book, I would not do that. It's confusing. For some reason, he decided this is the kind of the normal one that you use all the time. And so he didn't want to keep putting the bar over this because it's the normal one. But you agree with me, right? It seems backwards. You just have to remember that. And honestly, we will mostly use this one here. No, we're going to stick with the book because I don't want to get, you look in the book and there's a bar, and then in class there's not a bar. And in the homework and on the quizzes, I will make it extremely clear whether we're doing the bar version or not. In fact, I think one of the homeworks I'll say, calculate CM0 bar, and remember that that's in terms of LT, because it's just to remind you. Now, the two important things that we're looking at as far as the pitching moment that we keep talking about is pitch trim. Can we make the total pitching moment 0? That means either one of these formulas needs to be 0. And if you look in here, we can adjust things. We talked through this One of the ways that we can adjust things is by changing the tail setting angle here, because everything else is geometry. So we can tilt that tail up and down and either create an up force or a down force to balance out the other half of it. So we said, yeah, we can do that, and we drew a picture about it, right? So then the next thing is pitch stability. And that's why we want this thing here. This is CM alpha. Let's see, the guys need to shift over to that screen. This is CM alpha, so we're going to look at this formula here and see if we can make it negative to get the pitch stability. So let's write it over here. And let's draw a picture of what's going on here. So there's the aerodynamic center of the wing. Here's the CG. Here's the distances. Those are from the leading edge of the C-bar, or actually this datum can be anywhere we want to put it, because we're really interested in this difference according to the formula. All right, that is this minus this, which is this thing here without the C-bar. And then here's the aerodynamic center of the tail. And LT bar is that thing. So can we make this negative? Lift curve slope, positive. So here's the signs. What about this? Positive or negative? The way we've drawn it with the CG aft of the wing, this is positive. How about this? This is lift curve slope, so that's positive. VH bar is LT bar ST over SC bar, so everything's positive in there. And LT is positive as drawn. If we put the horizontal tail in front, LT bar is going to be negative, right? So this is positive with the H tail aft. And d epsilon d alpha is usually much less than 1, so this is positive. And we're going to just kind of neglect this. This is small. We're going to say that the thrust line is pretty much lined up. So can we make that negative? And if so, how do we do it? Everything's plus, plus here, plus, plus, plus here. There's a minus sign here. So we need to make sure that that second term, without the minus sign, is bigger than the first term. That's all it really comes down to. We want a negative number here. So if that thing's bigger than here, when we subtract it, we get a negative number. Check? So in the picture, what does that mean? What makes this number bigger than that? It means we want this to be small enough, because that's that thing. And we want LT bar, which is in here, to be big enough. And that includes ST. So LT bar or ST big enough. So that's really, that tells you the secret to design. That's not a secret. The strategy to making sure that your airplane is pitch stable is that the distance here, the CG is close enough to the aerodynamic center of the wing body, and you have a big enough tail far enough aft that you get a negative number out of this. So it's real easy to do. You build your airplane, you find out where the CG is, and then you just keep making the tail bigger and farther back until it becomes stable. But you put too much tail back there and you put too big of a tail boom, you got to have all this structure in there to carry it, right? So there's kind of an optimal optimization you want to go through. You want to get your CG small here so that you don't have to have that huge tail way back there for efficiency and aerodynamics and just structures and building it. So. Now, if you look at this, we're talking about making the CG close enough up here and the tail big enough. So let's say we've already designed our airplane like this. And here's our tail. So we've picked our tail area. We've picked LT bar, put it way back here so that we're stable. And we're good. And then we add a bunch of weight to the back of the airplane and we shift the CG back. Can it get unstable? If we make this distance bigger and bigger, it's going to eventually make this term bigger than this, and you're going to get a positive CM alpha. So in fact, there's a spot here where CM alpha switches from negative to positive. And we want to know where that is because we want to make sure that we don't load our airplane with cargo and people enough so that it shifts the CG back behind that point. And this thing, the point where CM alpha is 0, is called HN, and it's the neutral point. And I want to write out the definition, but really what it is, it's the CG location where CM alpha is 0, or you get that borderline neutral stability between positive stability and negative stability. So this is an important definition. I hope you're writing everything down, but make sure you write this down for sure. So we're going to define HN is the CG position giving CM alpha of the entire airplane 0. So it's neutral stability. And we want to know that spot so that we can avoid getting the CG back behind there. And it turns out that this is also called the vehicle aerodynamic center. Why? What's the aerodynamic center of an airfoil? It's the point at which the pitching moment of the airfoil, that pure couple, doesn't change with angle of attack, right? So CM alpha for the airfoil is 0. How about the wing? The wing aerodynamic center is the point about which you take moments, and those moments don't change with angle of attack. So the pitching moment does not change with alpha, so the derivative of Cm with respect to alpha is 0 because it doesn't change with alpha. Same deal here. We've said this is where the pitching moment doesn't change with alpha for the entire airplane. So it's the vehicle or the entire airplane aerodynamic center. But we call it the neutral point. Let's see, CG position given that gives neutral stability. So this is the neutral point. That's what it's called. But you may hear somebody saying, well, that's the vehicle aerodynamic center. They're just talking about that spot. So can we calculate that? Sure, because we have a formula for Cm alpha. So if we take this formula and look for that special CG location that makes this 0, we get it. That's the value that we're looking for. Where's my eraser? All right, so I'm going to rewrite this formula. But now we're going to look for that special CG location. That makes this 0. So now it's not just any general H, it's the special one that makes this 0. And you can solve for this, just algebra. Right, shove this thing over to the other side, add HN wing body to both sides, divide by A. And so you can calculate exactly where this thing is. You know where the aerodynamic center of the wing is, you know where your tail is, you know the lift curve slopes, and you can calculate it. That's really important to know for your airplane because then you know that make sure the CG is not behind that. How are we doing on time? Do we have a couple minutes? Yeah, the last thing I want to do is if we look at our formula for Cm alpha, we notice that this stuff here matches the stuff down here with the sign flipped. So we can substitute for this up here and come up with a simpler formula for Cm alpha if we already know the neutral point. So take this thing, shove that over to the other side, and we flip the sign. I think I did that right, didn't I? Oh, sorry, let's just jump back up to here. It's easier. Sorry about that. If we take this formula here, notice we have minus ATVH bar this, so all of this matches what's up there. So we can flip this over to the other side. And then that's what we substitute in up for here. And then we get the nice, neat formula. All right, that's the first term. And then we're getting this. And these two cancel out. Right, it's just algebra. Did I get you messed up by? So I just took this thing, I solved by moving this over to that side, get the minus sign, and then that whole thing substitutes up for there, and we get a nice, easy formula for CM alpha. If you know, if you've already pre-calculated this. And really, this formula is just saying, well, if the neutral point is behind the CG, then you get a negative sign. We'll talk more about that next time. Have a good weekend. Look forward to warmer weather.